So today we have kicked up physics instead of kicked up chemistry with graphical analysis of vectors. So join me, Pounce the Physics Cat, and as we'll see towards the end of the video and some different problems that I'll have available, we'll have good old Dewey Bear, Boo Boo Bear, and of course all their attempts to evade, Ranger Smith. So stay tuned for special edition of Kicked Up Chemistry, Kicked Up Physics, graphical analysis of vectors. Alright, today what we're going to do is take a look at how to graphically analyze vectors and use vector addition. Now a vector contains a magnitude, which a scalar only contains a magnitude as well. So a scalar would be, for instance, mass. Mass does not have a direction, miles per hour or any speed. It simply is how fast you're going. It doesn't give you the direction. If you have a direction with it, then it becomes a vector. So weight is always straight down towards whatever gravitational body is pulling on it. So weight would be a vector, and the analogous portion of speed would be velocity. So velocity is a vector because it has both magnitude and direction. So I'm going to go through a couple of different things, and you're going to need a couple of things handy as well as we go through this. You're going to definitely want graph paper, and the reason you want graph paper is because it has all of these X and Y lines already on there, those Cartesian coordinate system. You're going to want to have some sort of ruler with a measuring device, and you're going to want a protractor. Now it doesn't matter if you have little ones like these or larger ones like these, as long as you have a ruler and a protractor. So the first thing that we're going to do then is we're going to figure out ways to indicate direction. So there are a couple of different ways that we can indicate direction. You always want to start out with your crosshatch here and at least have the north on it. I'll switch to a different color just so that way it shows up a little bit better on the video. South, and of course west and east. So these are perfectly acceptable ways of indicating different directions. In fact, if you ever noticed outside, if you're watching like a Superman movie or Spider-Man, where they're working at the Daily Planet or the Daily Bugle, and they always have a globe outside. And the reason they have a globe outside is because that's how they would advertise. We bring you all information from all points of the compass, north, east, west, and south. And that's actually where the word news came from. And so if you were headed northeast, it means you would be smack dab halfway between north and east, 45 degrees. So just to make it kind of precise, I'm going to line mine up here. There's my 45-degree angle. And this direction then would be northeast. And again, if that's all it gives you, that would assume to be a 45-degree angle then. If you were northeast, well, that's halfway between north and northeast. So that would be 22.5 degrees. And quickly just marking it off, there we have 10, 22, 22.5. Northeast would be that direction, which would be 22.5 degrees. Now, the wind, when you talk about the wind is always the direction that it's coming from. So a southwest wind means it's coming from the southwest blowing to the northeast. So this would not be a northeast wind. This would be a southwest wind or a south-southwest wind, because that is the direction that it is coming from. So if I simply bring this vector down a little bit, because that's one of the cool things about vectors, is you can transpose a vector anywhere in space and time off a little bit. That's what happens when you're using a marker instead of a nice sharp pencil, this would be a southwest wind, because the wind varies a little bit, so they're not going to give you an exact direction that it's coming from on the compass heading. But you can transpose a vector anywhere in space and time as long as the magnitude and the direction remain the same. And doing the same with this vector here, this vector then we can see would be a southwest wind because it's blowing to the northeast. So wind is always the direction that it is coming from. Now I mentioned a compass and a compass heading, and there's a compass, and here's a compass as well. I'll actually point it to the north. So you take the compass, you put it in the direction that you're actually going to, and we could figure that out. But north in here is actually right in that direction. This compass needle got messed up and it's magnetized reverse, so it points towards the south instead of pointing towards the north. Kind of goofy, but it is what it is, and that's just how it happened to work. So I'm just going to put it so it's easy for us, so it's straight north. And let's take a look and see what the compass heading here would actually be. And if that is due north, that looks like it's about 254 degrees. So on the compass heading. So on a compass, due north is 0 degrees or 360. Same. Due east is 90 degrees. Due south would be 180 degrees. And then due west is 270 degrees. So that's as a compass heading. So for instance, if you're flying in an airplane and you're asking them for a vector, well, your vector is going to be your speed, which is the magnitude, the direction that you're flying, and also your altitude. So you have three components then with that vector: your speed, your direction, and your altitude. So instead of saying, hey, fly south-southwest, which would be in this direction, they would say on the compass heading, this is 180, this is 22.5. So they would most likely round that up and call it 23 instead of 225.5 or 202.5 degrees, but it actually would be 202.5 degrees on the compass heading. Now, when you draw a vector, there's a certain way that you have to draw it. You have to draw them to scale. And so let's just take a vector and convert it into a drawing so that way we can go through and actually graphically analyze it. Now, a marker doesn't work as well because you want to draw these as fine as possible. So mechanical pencil, it works really, really well. And let's simply draw a vector. So I'll write it out using a marker, and then I'll draw it out using a nice sharp pencil. So let's say that we are traveling 7.5 kilometers at 20 degrees west of south. Now when we have that, this is our reference direction, which is going to be due south, and we're going to travel 20 degrees west of south. And so I'm going to go ahead and I can kind of see underneath here my graph paper, so I'm just going to kind of copy off and draw in my crosshatch lines here, so that way I have my starting point. So there's the north-south line. So you can see why graph paper is very, very useful. And there's our east-west line. So the first thing that we need to do is indicate our scale. So you want to indicate your north, south, east, west. Again, at least north. The rest of them you can figure out because they should be the same for everybody. And we want to write our scale reading. So my scale, I'm going to say that 1 centimeter is equal to 1 kilometer. So I'm going to have to draw mine 7.5 centimeters long. So here's my starting point, my origin. Now I want to measure off 20 degrees west of south. So it makes it a little easier if you turn the paper this way, because again, we already have north, south, east, west. So it really doesn't matter if you turn your paper, we have our reference directions. And let me line it up so I have my north-south line and my east-west line, and I want to draw that 20 degrees west of south. So here's 10, here's 20 degrees. So you just put a little mark there, and now we have 2 points, because 2 points determine a line, point 1, point 2, and I have to draw that 7.5 centimeters. And notice on most rulers, they don't go all the way to the end, and the reason is it's very difficult to actually measure exactly to the end. So I'm going to put my 7.5 right on my origin, line it up right through that point, go from the end back towards the origin and back again, making sure I draw this as precise as possible, because what we're going to do is we're going to have our first vector, our second vector, and then our next vector, however many you have, is called your resultant. And you always draw these from the head to tail method. So the tail the first to the head, tail the head, and then you go from the tail the first to the head of the last for your resultant. So I don't want to change the length of my vector, the length of my line. So what I'm going to do is I'm going to take my pencil, I'm going to put it at the end of the line, I'm going to bring it down, over, and back again, and then fill in the arrow for the head of my vector. Now I have not changed the length of my vector. It should be exactly still 7.5 centimeters, which it is. So that's how you draw the vector. So let's go through a sample problem here then. A car travels 35 miles at 22 degrees west of north. It then travels 20 miles, 18 degrees south of west. Where's the car relative to the starting point? So these are all things that you should be thinking in your head after you read the problem. Number one, you want to figure out what your scale is going to be. You don't want your scale so small where your picture is only this big, because it's not going to be very precise. It's not going to be very accurate. On the other hand, you don't want it so large where you run off of your piece of paper. So not only do you have to decide on your scale, but you got to decide where you're going to start on your piece of paper. Draw vector 1 to scale, vector 2 to scale, draw your resultant, and then using your ruler and protractor, find the coordinates and the magnitude then of the resultant. Now, looking at my paper, here's my graph paper, I'm going to go ahead and put my north, south, east, west line coordinate in here. So I'm just going to go up to the corner up here, and I'm just going to darken this one up. There's due north, south, west, east. Okay, so it makes it a little bit easier to see. I use a marker for this part. There we go. And now I need to figure out my scale reading. Well, there's nothing that says that you have to use centimeters. We could use inches. Physics is one of them strange things where in physics we still use both English and metric units. So, you know, just looking at the problem, if we made 35 miles, well, if we made it 1 centimeter is equal to 5 miles, that's only going to be 7 centimeters. And getting my ruler here, that's not very large. I mean, that's only 7 centimeters, and then the other one's going to be 4 centimeters. But if instead, if we used inches, we could use inches. That would work. We just got to make sure we don't go off of our paper. So you know what I'm going to do? I'm going to make my scale in inches. And since we have miles, so you write scale, 1 inch equals 5 miles. Just like on a map, where you have the legend of the map, and you have to read then off your map, and you can measure the distance between 2 cities and then convert it to how many miles it is. That's the exact same thing we're doing here. So now we can just do the factor label method, also known as dimensional analysis, If you're still confused or you don't know how to do dimensional analysis, well, what you could do is watch my dimensional analysis video on Kicked Up Chemistry with Professor Leonard, and then you'll understand how to do dimensional analysis. So I have 35 miles and I have 20 miles. Now it's important that that decimal is at the end because that means that we have our nearest sig fig is to the nearest mile. And now on my scale reading, I want miles to cancel. Well, on my scale, 1 inch equals 5 miles. So I put 5 miles on the bottom, 1 inch on the top. "35 divided by 5 gives me 7. So I need 7.0 inches for the first vector. 20 divided by 5 gives me 4. I need 4.0 inches for my second vector. So it's going 7 inches, and it's 22 degrees west of north. So due north would be in this direction, 22 degrees west of that then. So I'm going to want to start somewhere down here, down in the corner of my paper, so that way I make sure I don't run out of room. So I'm going to put this point right there as my origin. So I put a little bitty dot there, kind of hard to see on the camera, but it's right there, and that is my origin. And then I'm going to switch to my pencil, and I need to make another mark that is going to be 22 degrees west of north. So due north, I need to go 22 degrees west of that. So putting my protractor right on those lines. Again, it's nice because they're already printed on the paper for me. Get it lined up just right. 10, 20, 21, 22. There's 22 right there. And so there are my 2 points. 2 points determine a line. Now on this ruler, since I'm using inches, it's only a 6-inch ruler. It's not going to work. I needed 7 inches. Not a big deal. I got a larger ruler. So I'm going to put the 7 on my origin. Make sure that I'm going to hit my 22 degree mark. Make sure I get it lined up here. So again, you want to be precise because this is how you're going to figure out your answer. And I'm going to go right to this end where the inch markings are, which is not quite to the end of the ruler, because again, end of the ruler, it's very hard to get right to that point, plus you might bump it a little bit, and messes it up. And now I'm going to put the head of my vector on. So now I've got vector number 1 completed. Draw vector 1 to scale. Now I'm going to draw vector 2 to scale. Now this is my new point. This is where I left off. And I need to go 20 miles, 18 degrees south of west. Well, this would be due west, and I need to go 18 degrees south of that. So taking my protractor, and I'm going to try to line it up because it didn't end exactly on the line. And I need to go 18 degrees south of it. So here's 10, 15, 16, 17, right there, 18 degrees south of west. And I need that one to be 4 centimeters long. I'm sorry, 4 inches long. So let me get it lined up just right. And look at that, just made it on my paper. Again, the larger you make this, the more precise and the more accurate you're going to be. And there's my second point then. This one is 7 inches, 7 inches, 4 inches, 4 inches. And now our resultant is from the tail of the first vector to the head of the last vector. So we're going to go from the origin way down here in the corner all the way up here, and that's my resultant. So line up that point, line up that point. Put the head of my vector on. And now I simply have to measure the length of it. And I am ending up with, it looks like, 8 and 1, 2, 3, 4, 5/16. So 8 and 5/16 inches. Now, the problem with using inches is we end up with this 5/16. That's why the metric system, each millimeter in there, it's a little bit easier and more precise. Typically in science, we don't like to leave things in fractions. We want to round to the proper number of significant digits. So I'm just going to convert 5/16 into inches, and this gives me 8.3125 inches. And just to double check, this one was 7 inches. This one is 4 inches, and this one was 8 and 5/16, so 8.3125. Now, using my scale reading, I can convert that back into miles, because I know that 1 inch equals 5 miles. So taking 8.3125 times 5 gives me 41.56 miles. Now we still need to make our angle measurement. And we have a couple of different ways, reference points that we could use for that as well. So I'm just going to, again, darken in my east-west line. I'm going to take my protractor. I'm going to use a larger one so it makes it a little bit more precise. Line it up right on there. And I am 10, 20, 30, 40, 39.5 degrees north of west. Now on the other hand, we could have went the other direction and measured from the north, and then we would have 10, 20, 30, 40, 50, 50.5 degrees west of north instead of 39.5 degrees north of west. Either way is perfectly fine. And so if this went all the way, I'll just draw that in. And again, that's just different ways of indicating directions. And so if I go all the way to that line, it would be 50.5 degrees. Now instead, we might want the compass heading instead. So on a compass heading, due south is 180, due west is 270 degrees. So this would be 270, and then we would have to add to that the 39.5. So 270 plus 39.5, that would be 309.5 degrees on the compass heading. And I'll write all of these down. Now, as far as significant figures go, we were given to the nearest degree and we were given to the nearest mile. So that's how our answer should be as well. So for our resultant then, our 41.56 miles is going to round to 42 miles. So it's 42 miles at, that's actually where that symbol originally came from, is at. Not used in, now it's used in email addresses, but it's been around since before email was around. And let me do the first direction here first. 39.5 degrees would round to 40, decimal at the end indicating that it's significant, degrees north of west. Because west would be our reference direction, we're going 40 degrees north of that. Now another way we could indicate it, it's still, the magnitude is the same, 42 miles at 50.5, so 51 degrees west of north, which would indicate that direction, or a third way, 42 miles at 309.5 degrees, so that would round to 310. We want the nearest degree, so I'll put a decimal at the end. And if there's no east-south, north-south, east-west after this, that simply means that's a compass heading. So that would be 42 miles at 310 degrees on the compass heading. And so we have taken our given information and we have resolved, hence the resultant, these two vectors, and we now know that if you traveled in this direction and then in this direction, those distances in those directions, that you would end up 42 miles at 310 degrees on the compass heading, or 51 degrees west of north, or 40 degrees north of west. Well, hopefully that explains how you do graphical analysis of vectors. Again, it's very similar to drafting. When you are drawing out drawings, not using CAD or computer-assisted drawing, but if you actually have to draw everything out with paper and pencil, this is exactly how you do that as well. And thanks for watching, and I'll see you next time.